on the final. Okay, any questions before we get started? Again, once we do here, what we do here is we go over the sample exam question by question, and we can talk about any questions you may have regarding anything. Our first question, we have a gas in a sealed cylinder with a movable plunger. We've seen that before. We're adjusting the plunger so the pressure on the gas increases. Temperature is remaining constant. And what's going to happen to the volume? This is a very simple Boyle's Law question. Remember what we said about Boyle's Law. Here we have our cylinder. Here we have a little tiny weight. Not much happens. But if we go and we increase the pressure, our volume decreases. Very simple demonstration that the volume and the pressure are inversely proportional. Now again, what that means is, the bigger the pressure, the smaller the volume. That is Boyle's Law. So let's go back to our question. Boyle's Law tells us pressure and volume are inversely related. If we're going to increase the pressure, what happens to the volume? Well, increased pressure. Oops. You know, I can't seem to adjust the gamma on this thing so that we can see this, but it decreases the volume. The projector just has a real issue. It doesn't follow anybody's gamma profile. But decrease is the magic word here. Any questions? All right, that's Boyle's Law. Let's do Charles. Again, we have our same cylinder. We're going to change our temperature, so the temperature increases. Pressure is going to remain constant. What happens to the volume? Remember what we saw with Charles's law. As we increased the temperature, we found the temperature and the volume were directly related. The larger the temperature, the greater the volume. Therefore, if we're going to increase our temperature, what happens to our volume? It simply increases. And finally, our third friend in the gas laws is Avogadro. We have our cylinder, but we're going to pump in more gas. If we keep temperature and pressure constant, and we're pumping in more gas, what's going to happen to the volume? Well, we got more of it. So it has to go up. The two are directly related. We're adding more gas. Therefore, we must increase our volume. Any questions? All right, those are the three major gas laws. I can promise you that on the exam you will see a derivative of these types of questions. Increasing pressure, increasing temperature, increasing number of moles, whatever. Make sure you understand the basic concept. Yeah?
What's number 3's gas law? What's number 3's gas law?
I'm sorry, which?
Number 3?
Number 3, that's Avogadro. But I would never ask you what Avogadro's law is. I don't do names. All right. Now we have a fun question. This is Charles's law. Which of these relates Charles's law?
No.
That was a different question on a different day. Don't fall for it. Charles' law says that volume and temperature are directly proportional. Okay? We said that. Directly proportional. So you increase the temperature, you increase the volume at constant pressure. So which of these represents that? Here's our little square. If our numbers are directly proportional, what we are saying mathematically is that volume is directly proportional, that's what that little sign means, to temperature. Okay? Now, several times when we've done the gas laws, we have said this. Anytime you have this proportionality sign, you can replace it with a constant and an equal sign. Proportionality can always be replaced by some constant, we could call it K, and an equal sign. So therefore, we're talking V is equal to KT. So which of these works? Well, clearly, if you could see it, V is equal to KT, of course, that works. Now think about the algebra on the rest of these. If we bring T up here, that's VT equals K. That doesn't work, does it? This one is nonsense. This is the two-state thing, but it doesn't even work for Charles. And here, VT equals K, same thing as this. This is the only one that is in fact Charles's law. Volume directly proportional to temperature. All right, remember the lab where we had this little flame and we put these things with salts dissolved in ethanol and we sprayed them in the flame, and it was so much fun. We got nice bright colored things out of it, and then we looked at emission lines from mercury, hydrogen, fluorescent lights, all of that stuff. Why do we see a color? That's what this question is. Why in the world do we see this color? It's the actual color of the element. Metal absorbs energy, promotes electrons to higher quantum levels. When they return, we get discrete wavelengths. Metal atoms are reacting with the flame to produce colored elements. Or metal atoms are reacting with CO2 in the flame to produce colored compounds. Now we talked about this in class, and basically here's the model that we presented. This is our atom with multiple energy levels that you might be able to see or not. When this absorbs a photon of energy, when it absorbs energy, these electrons that are in discrete shells can absorb that energy, and when they do, they move to a higher energy shell. So let's do that. They pop up, they're now up here that used to be down there. Now that's a very unstable place for them. They don't want to be out here, they want to be back home. So they will then return home, and as they do, they emit this energy as light. We see that as discrete bands for the distance, really, between where they started, where they go. They fall back down, emit this wavelength, and we see very discrete bands for the energy that was absorbed and then re-emitted. Because of that, and because every atom, every element, has its own unique set of orbitals and electrons, every atom, every element will have a different set of bands. And that's how we can identify the element very, very accurately. So, what we're doing here is we're going up, coming down, and we get light. If we go back and look at our question, it's the actual color. Well, that's nonsense.
B.
Not reacting with the flame, not reacting with CO2. Clearly, they are absorbing energy, promoting electrons, and then when they return, we get a discrete wavelength of light. Any questions? All right, well, this is just kind of a fun question. We use a device to look at these things.
Is it A, the other one, the previous one, the 5?
No, the previous one, the answer is B.
Oh, okay.
The answer is B. Again, these don't show up with this projector. I apologize for that, but it's not my fault. You can come look at my slides, they're perfect right there, but projector doesn't work. All right. The device we use to examine the spectral lines is what?
Spectroscope.
Well, it was an S word. We all remember it was an S word.
Spectroscope.
Stethoscope.
No.
No, that's not right. We
No.
weren't listening to anything, were we?
No, I said spectroscope.
Spectroscope. Well, that's an option. Spectrometer. What the heck is a spectrometer? If you Google it, a spectrometer looks like this. Now, nobody in the world would let you guys touch a machine that looks like this, would they? No, they wouldn't. Yeah, they wouldn't. So this one's out. Spectroscope.
Yeah.
We had an this is what it looked like. Yeah, that looks familiar, doesn't it? Spectrophotometer. What in the world is that? Well, this is a little baby spectrophotometer that you would use in general chemistry. What it does is it looks at absorbance of light at different wavelengths. But that's not what we used. What we used, you were correct, simply was the spectroscope, and that's option C here. Look in this end, and you bend it back and forth until you finally manage to figure out how to see the lines, but it works nicely once you get it figured out. Any questions? All right, we did another lab where we looked at conductivity. We talked about strong electrolytes, right? And weak electrolytes, and non-electrolytes. Well, a strong electrolyte will do what in water? Well, step one, yeah, it's got to dissolve, doesn't it? Otherwise, it doesn't do anything. So dissolve works. Dissolve and form electrocytes. Okay, what the heck is an electrocyte? Well, anytime you see a word ending in "site" like that, it's actually talking about a cell. Okay. When you do a site, you're talking about a cell. An electrocyte is actually the cell that generates the electric current in like an electric eel. So this is the electrocyte right here. You can see the array of them in the tail section. And this is what generates the great potential that the eel can shock you with. Now that's very interesting, but no, we didn't do electrocytes. Next one, dissolve and dissociate into ions.
Yeah.
If it doesn't form ions, it doesn't conduct electricity, does it? So this one is correct. It must dissolve and it must form ions, A and C are the correct answers.
Bang, bang.
Any question? All right, we looked at several solutions in that lab. We put oil in water, we put hydrochloric acid, we put sodium chloride, that's table salt, we did sugar in water. Which of these is a strong electrolyte? Well, if you look at A, solution of olive oil in water, if you've ever made salad dressing, they don't dissolve, do they? So you can't have a solution of olive oil in water. Hydrochloric acid, that's HCl, covalent compound, right? But, oh, here's the little thing that we used, remember? And looked at our lights. Hydrochloric acid. When you put the covalent compound in water, the bond is so polar that water is capable of splitting it into hydronium and chloride. It actually splits it, virtually all of it, into hydronium and chloride, and that is ions in solution. Sugar is also a polar compound, but water doesn't ionize it. It simply dissolves it, but doesn't ionize. So the sugar is a non-electrolyte. The correct answer here is simply solution of HCl in water. All right, remember our friend pH. I can remember way back being a child, and pH was very complex to me too. I was 5, but it was still very complex to me. If we have a solution that has a pH of 3, what in the world does that mean? Is it basic, acidic, is it neutral? Does it have 3 moles of acid or 3 moles of base? Once again, what does the concept of pH mean? This is something you can write on your card. Remember, you can bring a 3x5 card to this exam with anything in the world you want written on it. You know, people's phone numbers, formulas, whatever.
What's the length again? I'm sorry.
I'm sorry?
What's the length?
3x5. 3 inches by 5 inches, not 3 feet by 5 feet. Okay? All right, so what does this mean? Well, remember, pH is simply the negative log of hydronium. Okay? pH is the negative log of hydronium. So our pH here is 3. If we take the anti-log of both sides, we also remember, and perhaps write on our card, that 10 to the minus pH is equal to hydronium. So on your calculator, that's 10 to the x. So in this case, that would be 10 to the minus 3. Now 10 to the minus 3 is 0.001 moles per liter. Remember, anything that has more hydronium than 10 to the minus 7 is acidic. 10 to the minus 7 is neutral. Anything that has more than that is going to be acidic. Now you can also just remember this simple fact. If the pH is less than 7, the solution is acidic. If it's greater than 7, it's basic. If it's equal to 7, it's neutral. Any questions? Now, one of the favorite things to ask on this exam has to do again with pH. And this is a pH change. We are decreasing from 7 to 5. What is actually happening to the hydronium levels? Yeah.
So number 9 was that it was acidic.
Number 9 was the solution is acidic.
Thank you.
I'm really sorry that this doesn't show up. No. Oops. All right, so here we're changing a pH from 7 to 5. What's actually happening to hydronium? Remember, pH is a log scale. So every pH number is a power of 10. It's a log scale. Every number represents tenfold. We can demonstrate that going back to our formula. pH is minus log hydronium. And again, same thing, 10 to the minus pH is hydronium. So we're starting at 10 to the minus 7, and we're going to 10 to the minus 5. So, do we have more hydronium or less? Well, 10 to the minus 7 is a little tiny number. 10 to the minus 5 is a bigger number, isn't it? By how much?
100.
2 orders of magnitude. Minus 7 to minus 5, that's be a factor of 100. Any question? All right. One of the great funs of chemistry is getting to balance equations. Right? Here we have sodium nitrate, and it's decomposing to form sodium nitrite and oxygen. Now, as we look at this equation, we can immediately tell it's not balanced. As it's written, we do have 1 sodium on both sides, we have 1 nitrogen on both sides, but we have 3 oxygens here, and we have 4 on this side. So it's not balanced. Now, there are lots and lots and lots of strategies to balance equations. One of them that I recommend is the odd and even thingy. Here we have odd oxygens, here they're even. They must be the same on both sides. So let's make this guy even by putting in a factor of 2. That'll give us 6, that's an even number. Now we look and see what happens on the other side once we do that. We have 2 sodiums now, 2 nitrogens. Let's ignore the oxygen for a minute. 2 sodium, 2 nitrogens. Here we have 1 sodium, 1 nitrogen. Again, let's stick in a 2 so that the sodiums and the nitrogens work together. And now let's see what damage we've done to the oxygen. We start off with 6 oxygens. Here we have 1, 2, 3, 4. And here we have 2 more. We used 4 of them here, have 2 left over. In order to make it a decent question for a multiple choice, we have to put something in here, and 1 is our coefficient. We all know that normally we would not show the 1, unless, of course, it was an exam. Any questions? All right, we covered one of my favorite subjects, and that was organic chemistry. Didn't do much in organic chemistry. If you want to take it, my gosh, I highly recommend it. It really is the epitome of chemistry problem solving. Well, one of the things we talked about were functional groups. Functional groups are the things that make organic chemistry work. And that's because there are billions of organic compounds. But the functional group within any of these billions of compounds, they all have the same basic reactivity. So you can categorize them into like 20 groups. Makes it really doable. We're looking for a compound that contains only sp3 hybridized carbons. Now, when we talked about hydrocarbons, we talked about 3 basic hybridizations. We had alkanes, alkenes, and alkynes. The alkanes, we said, only had single bonds. Alkenes had at least one carbon-carbon double bond. And the alkyne had a carbon-carbon triple bond. You'll note that the valence of carbon, that's the number of things that's bonded to, is the same in all of them. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. So carbon is always bonded to 4 things. The alkane had a general formula of CnH2n plus 2, and all carbons were sp3. Alkene, CnH2n, and we have sp squared carbons. Finally, for an alkyne, we had sp. So going back to our question, what only contains sp3? Clearly, that is B, the alkane. This is the branch chain alkane. Again, we can have branches going everywhere, but every carbon is tetrahedral, every carbon is sp3 hybridized, and we only have single bonds. Any questions? All right, at the tail end of our organic chemistry lecture, we also talked about biochemistry. Remember that biochemistry really came from organic chemistry. And if you want a decent biochemistry course, it should be taught by a chemist, not a biologist. Amino acids contain what? A, contain an amino group and a carboxylic acid. Well, remember we looked at the structure of the 20 essential amino acids as we know them. Here are a couple. This is alanine and serine. They all contain a carboxylic acid group, and they contain an amino group. Hence the name amino acid. They also contain a carbon in the middle, and this carbon in the middle is attached to things. We'll call those side chains. This is a CH3 group. This is a CH2OH. They're all different. All 20 are different. They're all unique. And they all have unique reactivity. But they all have the amino group and the acid group. So, our first question, that is correct. Secondly, they can polymerize into short chains called peptides. We've heard of things called human growth factor, whatever. That's a peptide, right? Those are peptides. Going back to our amino acids, here we have alanine and serine once again. To make a peptide, you simply need to hook these guys together. We're going to do that by eliminating water. We're going to do 2 H's, 1 oxygen, and make a bond between the nitrogen and our carbonyl. This is what's called an amide link, also called a peptide bond by biologists, but it's an amide, and here's the water we split out. So this is a dipeptide. We can continue the process, stick on more and more. This is leucine, glycine, serine, alanine. This is a tetrapeptide. So yes, they can bond together and form short peptides. Insulin is an example of a peptide. They're the basic building blocks of proteins. Well, what's a protein? Well, it's simply a peptide that just kept going. Long chain of amino acids. This is phenylalanine, leucine, serine, and cysteine. Again, amino group, carboxylic acid group, and they're all linked together by the amide linkage. Finally, form the backbone in RNA and DNA. Well, remember what we said about RNA and DNA. Here's the double helix. Here it is expanded. We have bases, adenine and thymine up here, guanine and cytosine down here. Look at this. Do you see an amino acid anywhere? No. The DNA bases hydrogen bond to each other. That's how they pair up. Here we have a backbone of sugar and phosphate on both sides, but no amino acids. Therefore, the correct answers here are A, B, and C, and E is the correct response. Any questions? Let's go back to pH, our friend pH. Remember POH? POH was kind of invented by somebody with a sadistic streak, I think, just to confuse people. But there's a simple relationship between pH and POH. It's something that is worth writing down on your card because it is so simple. And at 25 degrees, it is always true. And that is pH plus POH is always 14. So if you know any pH value, if pH was 1, POH must be 13. If POH is 7, pH is 7. They must always add up to exactly 14. Any question? All right, let's do acid-base again. Which of these is a basic solution? Which is basic? Remember, we have acidic, neutral, and basic. First one, pH is less than 7. Remember our rule. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's basic. It's a simple rule. All right, so for our first one, pH is less than 7. No, this is an acidic solution. The lower the pH, the stronger the acid. H plus times OH minus is less than or equal to 10 to the minus 14. Well, that's just sheer nonsense. Just like pH and POH are always equal to 14, hydronium times hydroxide is always equal to 10 to the minus 14. Not less than, not greater than, it's always 10 to the minus 14. If hydroxide is greater than hydronium, now what are we talking about in the basic solution? We're talking about a little bit of acid and a lot of base, right? What's the base? Hydroxide. If hydroxide is greater, it's basic. If the two are equal, it's neutral. If hydronium is greater, it's an acid. Any questions? Well, we talked about Bronsted and his acid-base thingies, right? That deals with proton donors and proton acceptors. We also call these conjugate acid-base pairs. Now, what we have here is an equation. We're looking at only the forward reaction, so going this way. And we want the conjugate acid-base pair in the forward reaction. So the question you want to ask yourself is, on this side of the equation, what's the acid? What does an acid do? An acid donates a proton, doesn't it? That's what an acid does. Donates a proton. So of these guys, which one donates the proton? And when it does, what does it form? Well, here we have hydrogen sulfate, and we're going to sulfate. How do these differ? Well, this guy lost a proton, didn't it? That sounds a whole lot like an acid to me. Hydrogen carbonate. And on this side, we have dihydrogen carbonate. It didn't donate a proton, it accepted one. So this is acting as a base. So if we're looking for the conjugate acid-base pair, it must be the same compound, just missing a proton. So that's going to be hydrogen sulfate to sulfate. B is the correct answer. I'm sorry. A is the correct answer. I can't see it either. A is the correct answer. Hydrogen sulfate is the acid, and it forms its conjugate base, which is sulfate. Any questions? All right, let's change gears again. Let's go back to our friend the gas laws. We're dealing here with a single state gas law problem. That means we're not doing our cylinder thing, where we're changing from one set of conditions to another. We simply have a sample of gas, and we know everything about it except one thing. So we're trying to figure out the one thing that's missing. What equation do we use? We had two ideal gas law situations. One was single state, and one was two state. Two-state, again, is when you change something and you try to figure out what happened to some parameter. Single state, you just have it sitting there and you're trying to figure out the unknown. The rule we remember is that for a single state, we want to use PV equals nRT. Remember PV equals nRT, it's an internal line, must be a word for that. Easy to remember, to make a song out of it if you want. PV equals nRT. And by George, here's C is PV equals nRT. Well, that's simple. Except we have A and C and A, B, and C. All right, look at B. P1, V1, P2, V2. What is that? Well, that's a two-state right away, isn't it? This isn't quite Boyle's law. Boyle's law would be P1, V1, P2, V2. This is nothing, that's nonsense. Forget B. How about A? What if you took this equation and you multiplied both sides by RT? It would cancel on this side, RT would show up over here, and those two would be the same equation. Make sure you can do the simple algebra. This is PV equals N RT. Just like this one, A and C are correct. D is the proper response. Any question? All right, we did the question about conjugate acids and bases, and we had real live chemical things there. That's the easy one. This one is more difficult, because this just has words. Words are much more difficult than chemistry. I could never do English. Which is correct regarding an acid-base conjugate pair? Conjugate base will have one less proton, one more negative charge. Acid will have one more proton, one less. Conjugate base is formed by reaction with hydronium. Conjugate acid is formed by reaction with hydroxide, and of course the dreaded none of the above. Well, remember, and we wrote on our card, what we know about a conjugate acid pair. An acid will lose its proton to form its conjugate base. So it's going to lose a proton. It has to be the same compound. It just loses a proton. So as we look at these, conjugate base will have one less proton. Well, that sounds good. Conjugate acid will have one more proton. Well, that's not right. By reaction with hydronium, that's stupid. And D, well, that's even sillier. This is hydroxide. The correct answer, of course, is A. It will have one less proton and one more negative charge. Any questions? All right, this type of question generally shows up on the exam as something where you have to write down numbers and equations and stuff like that. So please pay attention to this style of question. We have a solution with a pH of some value. This is 12. Calculate POH, hydronium, and hydroxide. On the exam, I would want you to show the formulas that you use to get there, and of course the correct answers. Well, let's start off with hydronium. 10 to the minus pH is hydronium. That's already on our card. Now conveniently here, our pH is 12. So we can simply substitute 12 in here. And by George, this is our hydronium concentration. 1 times 10 to the minus 12. Simply substitute in for pH. Next, let's do pOH. Remember the question we had a bit ago. What was the fundamental relationship between pH and pOH? They always added up to what? 14. So if we know pH, we calculate pOH by simply subtracting, and the pOH is 2. Finally, hydroxide. How are we going to calculate hydroxide? There are 2 ways that we know. We can remember that hydronium multiplied by hydroxide is always 10 to the minus 14. That's where this comes from. Or we could sit back and say, well, hey, I know what pOH is. And just like this relationship, hydroxide is 10 to the minus pOH. So, all I have to do is stick in my pOH right here. And hydroxide is therefore 1 times 10 to the minus 2 moles per liter. Any question? And our last one here. If we know how many moles per liter of hydronium we have, and we know how many moles per liter of hydroxide we have, what do we know? Doesn't matter what they are, but we know them both. Things we remember. If we multiply these 2 together, the product will be 10 to the minus 14. Does that sound right? Yes, it does. Hydronium times hydroxide is always 10 to the minus 14. If we know the concentration of both, remember whichever one is larger determines if it's acid or basic. If it's more acid, it's acidic. More base, it's basic, so we know if our solution is acidic or basic. Finally, the negative log of each added together is 14. What is the negative log? That's the pH and pOH, isn't it? And we just did that. pH plus pOH is always equal to 14. So A, B, and C are all correct. Hydronium times hydroxide is 10 to the minus 14. pH plus pOH is always 14. All right, remember we have the exam and you have tutorials. This is the full list. You get 5 points for each of these. You get 10 points if you do combined gas laws. Oh, you all taking pictures. You're such good students. I'm so proud of you. Make sure you do as many of these as you possibly can, because It really does have a huge impact on your grade. 5 points added to your exam score. I leave it here for another 5 seconds. 4, 3, 2, hurry up. Now it's gone. Oh, okay, you're slow. Anybody else? It's also going to be on the